Okay, guys. So good afternoon, everybody. Welcome back. And let's not waste any time because today's lecture is gonna be kind of a I don't know. It's gonna be very huge in lots of sense. Um, but okay. So welcome back again. And here we go. Now we're gonna really dive in and look how
Assim, eu
the
tirei o que?
perturbation. Okay. Somebody saying something, asking something, I don't know. Okay, well, let's let's move on then. So I don't know if you guys are I'm not sharing the screen yet, am I? No. Okay.
No, not yet.
So, well, okay. So we're gonna really dive in and look how to do perturbation in short shoot. We spent last lecture kind of setting things up, right? And preparing everything uh to do this. So here we are with the main course, the main feature, the protagonist, maybe. Hmm. I have what I have planned for today. I guess I won't be doing all that I prepared for today. Maybe, maybe we won't have time, but I guess that we can do the master equations tomorrow. We will make we will trail the whole path to the master equations, and then we will find the master equations for the odd and the even perturbations tomorrow, okay? Which means to really get to these Reggie-Wheeler and Zerilli equations, which are the main goal of this mini course, okay? So let's go. Let's do this. So perturbations in short shoot. Equations here are gonna become very convoluted the most so far in this course, okay? So I guess we've been building some maturity, okay? We have been building some experience with convoluted equations, but anyway, bear in mind that any questions, any trouble with some passage, you can always send in a chat. Kyle, you have all the liberty to interrupt me any time that some question pops up in the chat, because it's important that we follow all of these steps, okay? So, okay, so previous lecture, we saw how to subdivide the perturbation functions, right? That will compose our perturbation tensor, right? Into the even and odd functions, which basically, how do you do this is you look at which is the basis for each function. If the basis for such function is an odd, right, is a odd basis vector or a tensor, right? And then he will be here, subdivided, he will be categorized as an odd function. And if the spherical tensor, spherical vector is even, that works in the basis, then the function that is multiplying this basis element will be even, okay? So there's no secret, no mystery. So, which means we can decompose our metric perturbation in the following way, right? Here we have the full metric perturbation, h mu nu, and we can split it into a even part and an odd part, okay? All right. So here we have the even and odd parts, right? So here we see that we have an even function k, right? Multiplying a even spherical tensor, which in this case is a scalar, is a 0, 0 tensor, right? A spherical tensor y. Here we have another even sorry. We have another even function, which is also multiplying the spherical harmonic, the scalar spherical harmonics. We have this, and you see why we have this relation, right? So the even functions are components per se of the basis of the even basis elements, right? Okay, and then we have the odd part, which is constructed obviously from the odd functions, okay? So here we have a odd vector spherical tensor, and here we have an odd spherical tensor as well. Here we have a tensor, a 0, 1 tensor, and here a 0, 2 tensor, okay? And here we have the odd functions, right? Okay, so now note that when we constructed the spherical tensors, right? The scalars, the vectors and the tensor spherical harmonics, we took first and second derivatives of the scalar spherical function, right? The spherical harmonic, okay? And these functions here, they are composed of the associate Legendre polynomials, right? And when we take first and second derivatives of these polynomials, they decrease in order in L, right? And this is a problem, which means that basically for these vectors to exist, right, L must be greater or equal than 1. Okay, this is a property of the associate Legendre polynomials, right? So if there is any question about this, I recommend that you guys take a quick look at some mathematical methods book or something like that. I mean, it's not very important to what we are doing. I mean, it is important, but the mechanics of the thing are the foundations, right? What constructs this is not very important right now, okay? What is important is that this happens, which means is that these vectors won't exist, right? For L less than 1, okay? So they must be at least equal to 1 or greater, okay? For these vectors to exist, okay? Because they are constructed from first derivatives of the scalar spherical tensor, right? And the same goes for these guys here, because these elements, they are constructed from second derivatives of these elements of the spherical, the scalar spherical tensor, right? Which means that they won't exist for L greater or equal than 2, right? So what this means is that basically for we to have a complete basis for all scalars, vectors, and 0, 2 symmetric tensors, as we are interested in having, we must do perturbations for L greater or equal than 2, okay? And you know, this is not a problem, because as we investigate what these numbers mean, right? The L equals to 0 and 1 have nothing to do with gravitational waves exactly per se, right? The L equal 0 perturbations, right? Perturbations, what I mean, because L, remember that the H's here, they are all concerned also with L and M, right? So the perturbations here for L equal to 0 will be related to the increase or to the change of black hole mass, right? So perturbations that are constructed, that are caused by some source that is constructed from a monopole, right? Will only affect, right, the black hole mass. Perturbations generated by some dipole, right, will be related to the change, or maybe to the black hole acquiring or losing angular momentum, right? And then only when we go to the quadrupole, right? When we divide this in multiples, and only when we go to quadrupole, right? We see that there is some relation to the gravitational radiation. We didn't discuss this, right? But if you go to the reference by majority, you will see this discussion there. I think that Ferrari and the Berti also do this discussion about the energy of gravitational radiation and the source of it being a quadrupole moment. Okay. But this is out of the scope of this mini course. All that I'm saying here is that we maintaining to L greater or equal than 2 doesn't mean anything for us because we're not losing anything, okay? Not losing anything because we are focusing in the gravitational radiation, right? Okay. So let's take a quick look at a quick reminder of what the Schwarzschild background looks like, right? So the geometry for the exterior of a spherically symmetric body of radius r is given by the Schwarzschild metric here in spherical coordinates, okay? Where this function f in the Schwarzschild metric will be taken as this, where 2m is the Schwarzschild radius, right? So the Schwarzschild radius is a property, right, of these spherical objects, okay? So the Earth, for example, has a Schwarzschild radius. The moon has a Schwarzschild radius. Stars have Schwarzschild radius. And what it means for this, you can ask yourself, you may wonder, well, how, okay, so this is a geometry on the outside of a spherically symmetric object. But how do I know if it's a star or a planet or a black hole? How do I know that? Well, the analysis basically, very roughly speaking, right, involves the relation between the radius of the object and the Schwarzschild radius. Okay, so very roughly, very not rigorously speaking, if you have a radius less than the Schwarzschild radius, you have a black hole, okay? So this is not 100% accurate. You have to take other things into account, obviously, but this is a good way to have an estimate, at least, okay? So, okay, we also here we defined the omega as the differential volume on the two sphere, right? The differential, I mean, I'm sorry. But yeah, I'm sorry. So the differential of with regard to the two sphere metric, okay? So once again, remember that we did spend a little time in the previous lecture talking about gauge symmetries in general relativity, right? Because we wanted to simplify, we wanted help to simplify our equations because the equations as they are at first, they are very complicated, very convoluted. So we needed a little help to simplify them, right? And we discovered that we could use some gauge freedom, right? There was an analog for GR, right? For what it means to have a gauge freedom, which is related to the invariance under coordinate transformations, which basically is equivalent to in GR at least to having an invariance under a group of diffeomorphisms, infinitesimal diffeomorphisms. Okay, so once again we turn to these gauges so that we can simplify our equations, right? So if we perform an infinitesimal diffeomorphism here, there's a I missing here. Well, I'm gonna correct this before I send to you guys. But yeah, so here is the transformation generated by this vector, this vector here, right? So we can do this infinitesimal diffeomorphism. We can calibrate this vector in a way that we can simplify some our equations. And in this case, we can set this elements here, here, and here equal to 0. Okay. So if we remember who they are, right? So we're gonna set these two functions, these two even functions of t and r equal to 0, and also this odd function. Is that it? Is that it? Let me just check if this is our yes. Yes, okay. So yeah. So we're gonna set this all equal to 0. If you're wondering what this vector should look like, so this could be possible, you can always check also the reference by Ferrari. They do these calculations there. But basically you have to solve a differential equation to find who these vectors must be so that we can set this. There are a number of different gauges, right? There is a Chandrasekhar gauge, there is the harmonic gauge, there are a lot of different gauges, right? The choice of gauge, it's entirely up to the problem, right? So depending on the problem, you choose some specific gauge, right? Using the gauge freedom, you can choose any number of gauges that exists already, okay? So, which means that you see that this function here, this function, they had two parts, right? They had a even part and a odd part, remember? So here is this vector function, right? Vector with respect to t and r, but a scalar with respect to theta and phi, right? So it has two versions, right? It has an odd version and an even version, right? But we are setting the even version equal to 0, right? Which means that basically there is only one now, which will, for sake of notation, to not be very messy notation, so that we don't have very messy notation, we relabel it, right? So since there is only one now, in such a way that it is defined like this, okay? So it's a vector with respect to t and r, right? So there is a 0, a HLM 0, and HLM 1, okay? In this gauge, what we call, oh, I'm sorry, I haven't named this, right? This is important. This is what we call the Reggie-Wheeler gauge, okay? Where we calibrate this vector enough so that we can set all these functions equal to 0, okay? This will simplify a lot of our equations. This is the Reggie-Wheeler gauge. And in this gauge, so let's go, things are gonna get serious from now on. So if we decompose, so remember we had this, right? We're decomposing each of these functions now. So this is a tensor with respect to t and r, right? So let's decompose this tensor, right? Harmonically. So here we have what this functions, this tensor with respect to t and r looks like. So these are all functions, h0, h1, and h2 are all functions of t and r, right? F is exactly the f from the Schwarzschild metric, right? F, which in the case of a Schwarzschild metric is equal to 1 minus 2 m over r, right? This f here. Let's just make sure that you guys remember where they come from. They come from the metric, right? And we construct our perturbation in such a way as to make so that the metric, the line element will look very much will look a little more friendly, okay? But we'll get there. Okay, so this is how this guy looks. This this will be the mixed, right? The mixed tensor, right? And this is how it really looks, right? So, which is basically taking the product of the vector HLM capital A with the basis in YA, right? Okay, so remember that these are the components of the vector, of the vectors, of the spherical vector that we constructed from first derivatives of the scalar spherical harmonics, okay? So that this guy who is a scalar to TNR, right, transforms as a scalar for TNR, but that is a 0 to tensor with respect to the sphere, right? He is constructed like this, okay? So see that here we have a scalar function. Here we also have a scalar function. Here are the bases, okay? Okay, so in this gauge, it will look like this because now remember that here we would have two options. We would have two copies of this same tensor, right? If we hadn't used the gauge, this would not be zero, which means that this would have a version for odd and a version, an even version, an odd version and an even version of this matrix, right? But since we took this vector completely to zero, right? So then all we have left are the odd parts, okay? Okay, putting them all together, we can reconstruct, right? Our metric perturbation, okay? Which will look like this. I know it seems a little bit scary, but bear with me. We're gonna decompose in a more friendly way in just a moment. Just put this here so you can look. This is the full metric perturbation in the Reggie-Wheeler gauge, okay? It would look a lot more, it would look a lot bigger if we didn't use the Reggie-Wheeler gauge. We would have another terms here. But these stars, they just mean that they are symmetric, right? So this, which would be a 0, 1, a 0, 0, 1, 0, a 2, 0, right? Is equal to the 0, 2, okay? This component is equal to this. This component is equal to this component is equal to this, and this is equal to this, okay? So this is just to save some space, right? Which means that this block here is exactly the same as this block here, but transverse, right? Okay, so remember that we saw that we can decompose this into an odd and an even part, right? Which is basically following the same reasoning that we did it earlier, right? So okay, this is the full metric perturbation in the Reggie-Wheeler gauge, but we've seen that we can decompose H mu nu based on parity, right, into an odd and even parts. This is the odd part, right, composed only of odd functions and odd bases, right, which leaves the even part to be like this. If we sum these two matrices, right? If we sum them, we regain this metric perturbation here, right? It's just taking the sum. Okay, so remember also that in the references, you may find this being called axial and polar, right? It's very common to find this. So I'm just putting here so that you won't forget, okay? So what we have in mind now, instead of working with the full metric and putting them all in one Einstein equation and with all these components, we separated into an odd and even parts such that we can now reconstruct two different line elements, right? Remember that the line element is constructed from the metric, right? The full metric, which means remember that when we saw perturbations in flat space-time, that the intuition behind what happens to that arrangement of particles in a circle well, the intuition came from the line element, right? So here we can reconstruct, if we substitute this into the line element, right? Then we have the odd perturbed line element, right? So we didn't plug in the full perturbation, only the odd part, right? Which would be basically similar mechanically and mathematically to what we did with the polarizations, right? With the different polarizations. I'm not saying that these are different polarizations necessarily, but mathematically they are two different. When we added the cross polarization, we had one line element, and when we added the cross polarization, the plus polarization, the cross polarizations, we had two different line elements, right? And the same is happening here. So here we plugged only the odd part, right, of the metric perturbation, okay? And we obtain this metric, which is to take the line element from Schwarzschild. So here you can substitute the full Schwarzschild metric, right? So let's just remember. So here we have.
Obrigado, viu? Bom trabalho pra você.
Is there some? I'll ask you, please, guys, to mute, please, your microphones, so that there are no interference, because I always thinking that that there is some question and maybe there aren't. So please, if you could, so remember to turn off your mics as you enter. But okay, so this is the Schwarzschild line element. So when we do the perturbation, here we have the full line element here, but we added all these terms to the line element of the Schwarzschild metric, okay? Which are, in this case, all off-diagonal terms, right? All these terms are off-diagonal, okay? So this is the line element, so we can see which are the components. With this line element, we can gain some intuition about which components of the Ricci tensor, the Einstein tensor, will be important for the perturbations, right? Which will be directly related to the perturbations. One way to do this is to construct this metric, right? Construct this this line element, right? And substitute this into the Einstein equations, right? So instead of constructing the versions of the perturbed versions of the Christoffel symbols, and then the Riemann tensor, and then from the Riemann tensor the Ricci tensor and the Ricci scalar, and so on, exactly as we did for the flat background. Okay, but we're gonna do this in a more I mean, I guess a more approachable way, a more friendly approach. So, and from this, exactly as we did here for the odd part, okay, we can do the same thing for the even part, right? Which is basically gives us this, right? So this is the even line element. So the line element as the even part of the metric perturbation passes if they were separate, if they were not part of the same gravitational perturbation, right? So if you could plug in just one of them, the even part would look like this, okay? So you can see that for the 0, 0 component, we added, because we already had it an f dt. Now we summed this component here, okay? For the 1 part as well, and the 2 part, 2 and 3 parts as well, and an off-diagonal element here, okay? Which has these two attached to it, because is symmetric, right? So the dt dr is equal to the dr dt, okay? Which is basically due to this term, this component here, okay? So now we have the two line elements. We have the odd line element, okay, with only off-diagonal terms, and we have the even line element with diagonal terms and off-diagonal terms as well, okay?
Hey,
Okay,
Vitor,
now,
there's a question in the chat.
okay.
João Pedro asks, by now we have removed the unphysical degrees of freedom, correct? So all of those matrix elements have a physical meaning?
Yes, yes. Excellent question. So yes, here I haven't been very I didn't say it right, but the Reggie-Wheeler gauge, it's the full gauge. Okay, so with the Reggie-Wheeler gauge, where is it? Is the Reggie-Wheeler gauge? So here we used all the gauge freedom we had. Okay, so there is no more help coming. Okay, so all the degrees of freedom here are physical in in some way. Okay, and we're gonna see that they all become part. They are all used to construct the master equation. Maybe we will see this today. I think not. I think maybe this will be left for tomorrow. But at the latest tomorrow, you will see how all these elements will play a part in constructing the master equations, which is the version for this problem, right? The version for this spherically symmetric curved space-time, the version of the wave equation, okay? For this curved spherically symmetric space-time, okay? But yes, excellent question. All these degrees of freedom have physical meaning, right? Okay, so let me just remember where we were. So here, right? So these are the two line elements, right? And the idea now is with these two line elements, we can, and these two metric perturbations, we can construct the even part and the odd part of the metric. You may wonder why we can't do this. We cannot do this in classical general relativity, the classical theory, right? Because the equations of motion in the Einstein equations, the Einstein equations are they are highly nonlinear, right? But now, what we have here, what we did in the second lecture, if I'm not mistaken, we linearized, right? We found the linear version of Einstein's equation. So now we can do this, right? We can open this up, and we can open the perturbations, the ages, the age that are inside these tensors, we can open them up, right? We have differential operators in here, second and first and second derivatives of the metric perturbation, which are linear operators, right? So if we decompose our metric age into age even and age odd, then we can separate them easily because we linearized it, right? We found it. We found yesterday the version for curved background, what it looks like, the Ricci tensor, and so on. So we found the linearized Einstein equation. So this is why we can do this in general relativity, out of the perturbative approach, the perturbative regime. We cannot do this because the equations of motion are highly nonlinear. Okay. But before everything, before we engage into constructing the Einstein equations, the Einstein tensors, since our background, right, is space-time is static, what I mean by that is that we have no time dependence, right, in the metric, not in the background metric, at least, right? We don't have a time dependence in the components of the Schwarzschild space-time, right? Let me just, so here, we see that we have no time dependence here, okay? This is a type of black hole that does not evaporate, right? We are not, this is classical general relativity, right? We're not considering quantum effects or semi-classical effects of any sort. okay? Which means that we can do a Fourier transform, right, of the metric perturbation and separate our time dependence easily by this Fourier transform here, okay? In such a way, let me just put this here, in such a way that we can transform every single function, right? So as we take this this integral over the omega here for every single frequency, we can do this for every component, right? These are linear equations. This is what is important to remember. Now we are allowed to do this because these equations are linear, right? This is the linear version of Einstein's equations. So we can deal with this and forget the time dependence for at least for now, okay? And the same goes for the even part, okay? So the tilde here, right, represents the Fourier transformed version of the tensors, right? Here. I guess I made a mistake here. It should be mu nu here and mu nu here, right? It should be a tensor. This is basically a scalar as we are looking at. So I'm sorry for the mix-up here. And once again, I will correct this before I send them to you. Okay, I promise. Taking advantage of this moment, I did not send yet the slides for yesterday's lecture. Okay, I had to do some things of my research. I didn't have time to correct them all, and because I also had to have some corrections of the slides from yesterday's lecture. And so in order to not send them uncorrected to you guys, I left them to send today. So after this class, after this lecture, maybe I can correct both of the slides from yesterday's and today's lecture, and I will try very hard to send them to you tonight. Okay. But okay, so this will be the transformed version of the perturbations, the Fourier transformed versions, right? When these Fourier transformed versions have a dependence of omega instead of t, right? Which is now what we will use these functions, okay? This is the functions that we will use, okay? So, but we will omit the tilde for simplicity notation, okay? So from now on, when we are talking about H, we're talking about the Fourier transformed version, okay? So we functions of omega instead of t, okay? Omega, r, and theta and phi, okay? So now note that for the odd Einstein equations, right, the odd line element here, remember that we constructed the odd line element, the perturbation terms are only off diagonal, right? I told you guys that this would give us some intuition into which components we would really use, right, to construct the Einstein equations, right? The perturbed Einstein equations, right? Because here in the full metric, the full Einstein tensor uses this whole metric here, right? But the unperturbed part, which is the g mu nu without the delta, right? Remember, they use only the components of the metric that are in here, right? Okay, so the delta g mu nu will use only the terms that are perturbative, that are in first order in age somehow. Okay. So you see that these terms, the perturbative terms, in the odd Einstein metric, in the odd Einstein line element, okay, in the odd line element, they are only off diagonal terms, okay, which means that as the perturbed Einstein tensor is concerned, as far as the Einstein tensor is concerned, the terms with the diagonal terms here note that these terms here will go to zero, right? Because the background metric doesn't have any off-diagonal elements, right? So even though this term here has elements from here that are off-diagonal, right? This here will go to zero. This element here will go to zero because the background metric here is a diagonal matrix, right? The Schwarzschild metric, it's purely diagonal. Let me just go back so you can see. So look, this is the Schwarzschild metric, right? The line element, right? But these are the components of the metric tensor, right? So in this, all of them are diagonal elements, right? So they're completely diagonal. It's a diagonal matrix, okay? Can be represented as a diagonal matrix at least. Okay, which means that it simplifies a lot the Einstein equation here, right? And this is important because we have a different approach in terms of the references. I think the most famous references, which are the core references, the main references for this mini course, which are the book by Ferrari, Paulo, and I don't remember the names of the other authors, but I remember Valeria Ferrari and Paulo Pani, right? So the book General Relativity and its Applications from Ferrari and Paulo Pani, they use these equations, right? First of all, they solve for vacuum, okay? So they solve far away from sources, they solve in complete vacuum, right? So even the source of perturbation, we're looking at the equations far away from the sources of the perturbations as well. So we have complete vacuum, right? And she uses this reference, this equation here, right? The book by Valeria uses this equation here when she goes to Reggie-Wheeler, when she's trying to get to Reggie-Wheeler equations, right? She solves for the vacuum solutions. And she does this for the odd Einstein equations. What I'm trying to do here is show to you that this is exactly, for the odd part, is exactly equivalent, right? Exactly the same. It doesn't change anything because as we move to the course by Emanuele Alberti, right? If you check the black hole perturbation course from Emanuele Alberti, he constructs the full Einstein tensor, right? He does not uses this equation here. He uses the full Einstein equation, right? For the odd part, this is completely equivalent, right? The results for both parts will be equivalent in the sense that what Valeria obtains for the even part, right, of the perturbation, the equations themselves are not the same as Berti obtains for the even part, but there is a combination of the equations obtained by Valeria that get you from Valeria to Berti, right? There's a bridge between them, right? So the results will be completely analogous, but the paths are different, right? So be careful with this. It took me a while to see why this could be done in so different manners, because at least for Reggie-Wheeler, this is completely analogous. And I believe that what happens for the even part, which the book by Valeria doesn't get in very much details, is that the equations that she obtains by some combination go to the Berti equations. Okay, so be careful when you're checking both references, right? If you want to be safe, I would recommend to go with this approach, right? To construct the full Einstein tensor. So there is no question if you lost any information, right? That could be contained in this term here, right? So if you have any doubts about which way to go, I would recommend to go the full way. construct the full Einstein tensor, right? And Berti does for in both regimes. He does for vacuum, and he does for sourced terms. Right? A sourced equation is, and he does the homogeneous and the non-homogeneous versions. And we're the way that I'm going to do this here is try to do the source version, because then everything the homogeneous version is easy to obtain, is only to set this equal to 0. Okay. But to do the sourced version, we have to prepare the source, right? The same way that we did with the metric perturbations, right? The right part and the left part of the equation must be constructed in the same way, right? So this perturbation, this tensor, this perturbed energy momentum tensor can be decomposed also into an odd part and an even part, right? And the decomposition is exactly analogous to what we did. We have more terms here because we didn't use the gauge to remove the terms here. But since some equations will have a 0 from one part, the correspondent components from the left or right hand side will also be 0, right? But only so that we don't lose any information and we construct this the most general form possible. Okay, we do it like this, right? In the Reggie-Wheeler gauge, we would set it this and this and this and this equal to 0 a priori. Okay, and we'd have only this and this part of the odd metric of the odd energy momentum tensor, right? And the even part looks even uglier, right? This is completely general, right? This in here we haven't imposed any gauge. This is the completely general energy momentum tensor, the even part at least. If we didn't use the Reggie-Wheeler gauge, the matrix for the H mu nu even, right, for the even metric perturbation would look exactly like this. We would substitute this by the appropriate version of the function, the H01, and so on and so forth. But the Reggie-Wheeler gauge allowed us to set some of these elements equal to 0. Okay. Bear in mind that everything that we do in the left-hand side, which we are going to start doing now, which is basically what is happening inside the Einstein tensor, right? Which is in the left-hand side of the Einstein equation, will also be done to the right-hand side, right? Everything you do in one side, you do in the other. Okay. When you have vacuum, Valeria only does these developments in a vacuum regime, which is much more easier to do because you don't have to worry about what is happening to the other side. You don't have extra terms that are multiplied in the left-hand side because it doesn't make a difference because you set this equal to 0, right? But here we have to take care of the right-hand side. So everything we do in the left-hand side will be done to the right-hand side. I mean, with the energy momentum tensor as well. So everything we're gonna do to separate the radial parts from the angular parts in the metric perturbations will also be done to the energy momentum tensor, right? So for the odd/axial part of both references yield the same exact equations since this is completely equivalent. Berti constructs this tensor and Valeria constructs this tensor here, but in the odd case, they are completely equivalent. Okay, because the odd perturbation is composed strictly from off-diagonal terms in the line element. Right? So remember that we constructed the curved version of the perturbed Ricci scale, the Ricci tensor, right? So decomposing harmonically the Ricci tensor as we did for the metric perturbation, right? We obtained this, which we already are familiar with from last lecture. So we're gonna see what this looks like. So we first did this for this tensor here, right? For the age, okay? So what we are doing now, we are plugging into this, into here, we're plugging the full perturbed metric, okay? So this is the full Ricci tensor, right? Perturbed Ricci tensor. I'm sorry, the full perturbed Ricci tensor, right? Which means that there is an odd part and an even part inside here, right? Plugging the whole perturbation, right, which we decompose in such a form, taking the covariant derivatives, we get to this tensor here, right? Which is the perturbed Ricci tensor, okay? And now we're going to look how this matrix is this 2x2 matrix, right? After all, this is we are working in a 4-dimensional space-time. So this is a 4x4 matrix. This could be represented as a 4x4 matrix, which means that this is a 2x2 matrix. This is a 2x2 matrix, and also this, and also this. Okay. So let's take a look how they look like. Okay. So what we did here is just multiply this by 2, which is the same. We just multiply both sides by 2. Okay. So this, which is the first quadrant here, can be decomposed as such, right? Where these are functions of T and R. These capital A's here, they are functions of T and R, right? Which contains combinations of the first and second derivatives of the metric components, right? We will see how they look like in just a moment. Okay, so all of them are multiplied by y, okay, which makes sense, right? Remember how the perturbation looks, right? We're taking these components here, taking the first and second derivatives of these components here, right? Which are multiplying the scalar spherical harmonic, right? So this is what is happening here. Encoded into these functions are the first and second derivatives of the metric perturbations, right? So the second quadrant, the second and third quadrants, right? Which is basically this two here, which are exactly the same, since this must be symmetric, a symmetric tensor, are constructed by this, right? So you see that we are in here, we have alpha, which is an even part of this tensor, and here we have the odd part of this tensor. Okay, and here we have a completely only even parts. This part of the Ricci tensor is exclusively even, right? All these functions are even functions. All of them are multiplying an even basis element. So in this we have a mixed, right? We have it mixed here. So this is the even part and this is the odd part, right? Okay, and inside here we have obviously we have first and second derivatives of the even metric perturbations, and inside beta we have first and second derivatives, combinations of first and second derivatives of the odd metric perturbation components, okay, which multiply this here multiply this basis element, and this, and the odd part multiplies an odd vector, okay. And what is left is the fourth and last quadrant of this tensor here, which is constructed as such, right? So here we have a traceless part, okay, and here we have the trace part, right? Remember that these two tensors are traceless, okay? Which means that these two elements here construct the trace part of this tensor, and this element here takes care of the trace part of this tensor here, okay? So in here, inside A3, we have first and second derivatives. Inside S and inside T, we have first and second derivatives of the metric perturbations. Okay? To see, to obtain them exclusively, to get rid of the rest and look at, exclusively at each of these ones, we have to do the separation, right? We have to make use of the orthogonality properties of the spherical tensors to separate them, right? If we were working in vacuum, right, we could only set them all equal to 0 and we would have our solutions, right? We would have our equations, because since this forms a basis, each one is linearly independent from one another, right? So basically all we had to do is set this equal to 0, set this equal to 0, this, and all these four functions here equal to 0, and we would have all the equations that we need, the odd and even equations, right? But it's not that simple when we're working with the source, right? When you are not working in a homogeneous equation. So this is what the betas look like, okay? And this is what the T here look like, okay? Which basically are the odd equations, right? Let's remember that these are all even functions, right? This is multiplying in an even vector, so it's even, right? It contains first and second derivatives of even metric perturbations. This also contains even first and second derivatives of the perturbations, because they're multiplying an even basis element. This also is even, since this tensor, it's even, right? So we have two here, right? For A going from 0 to 1, and this T, right? So we have three odd equations, which basically look like this, okay? Is it clear where they come from? This is a result of this, right? We plugged in, this metric here into this equation, right? Into this equation here, took the covariant derivatives, right? Where we computed the Christoffel symbols and all that comes with the covariant derivative, took the partial derivatives with respect to R and T and all that sort of thing. And then we end up with this, what we did was, let's group everyone, let's put together everyone that is multiplying, that are multiplying this vector, everyone that are multiplying this vector here. So we separate it like this, right? And this is what we got, okay? So this is what we get when we plug in the odd perturbations into the Ricci tensor, take the covariant derivatives, combine them as the Ricci tensor demands, and this is what it spits out, okay? These are the three odd / axial vacuum equations. To be a vacuum, you only had to set this equal to 0, right? If we set all these equations equal to 0, we are working in the vacuum. But since we want to see how these equations look like with the source, right? We have to perform the separation, right? We have to use the orthogonality properties and separate each one, and do the same with the other side to see which components of the energy momentum of the perturbed energy momentum tensor correspond, will source each of the equations, right? Which element of the energy momentum tensor will source this one, which will source this, and which will source this, okay? For vacuum, for vacuum, we set all this equal to 0, and we start simplifying the equations and what we will do next lecture. But first, let's take a look at what happens to the sourced equations, right? So far, let me pause here and see if there are any questions on how we got here. Are there any questions about how we got here? Is there anything on the chat that I'm not seeing? No? Okay, so I will take that as a, well, as a, okay, everything's good. I know that this all will not become quite 100% clear at first sight. Oh my God, so now my computer just jammed. That's nice. Okay. 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 Let me go back. Yeah. Sorry, guys. My computer, it's giving me a hard time again. Let's share this again. Only one moment. Okay, we are back. Okay. So okay, if there's no problem so far, so I will proceed. So for the source terms, for the source version of the Einstein equations, we need to appropriately separate the angular parts. Okay. And to do so, we need to make use of the orthogonality properties, right? And to do that, we will multiply some equations, right? Some components of these Ricci tensors here, we will multiply by some terms and combine one term with another so that we can construct the orthogonality properties, right? And then we're gonna integrate over the two sphere so that we can separate them, right? If you guys don't remember the orthogonality properties, don't worry. I only ask you to look into them for tomorrow's class, okay? So that what I'm gonna do now becomes clear, very clear, because I'm gonna repeat them for the Zerilli version, for the Zerilli equation, for the even part. I'm gonna take care in this lecture of the odd part of the equations, which are much more simpler. And tomorrow, I'm going to repeat them for the even part. But it's important that you understand what is happening here, okay? So what we're going to do here for the odd equations, right? You see that the odd equations are beta 0, beta 1, and t, which basically correspond to setting this equal to 1 and 0, and right, to obtain this part here, okay? This equal to 1 and 0. This is free, right? Because this can be 2 or 3, right? But again, what we can do to separate, for example, the odd part, right? If we take this vector here, right, which is part of the mixed tensor, right? This is part. If you set a equal to phi, okay, setting here a equal to phi, and multiplying this vector by this element here, which is basically the partial derivative with respect to theta of the complex conjugate of the spherical harmonic divided by the sine theta, and then setting a equal to theta and multiplying by this element here, which is the same as here, but the partial derivative now is a partial derivative with respect to phi. and then subtract these two expressions. So this element multiplied by this element multiplied by this, and then subtract one another, and then integrate in the, and then if we take it integrate in the two sphere, what is happening is this, okay? In the left hand side, what is happening is this, okay? I'm sorry. Sorry, guys. So what this is exactly the mathematical representation of what we just explained here, okay? We took this this vector, right? Which is part of the full of the tensor delta R A, capital A, small caps A, the mixed part, multiplied by this, took this part of the tensor, multiplied by this, subtracted one another, and you can see at home, you can reproduce this and see that what happens is exactly this, okay? What happens is that we apply this multiplication, right, to both parts of this. Remember that this is composed, if we set this equal to theta, we're going to have alpha capital A multiplying y theta plus beta A multiplying s theta, okay? And then we multiply this by the partial derivative. So this multiplication is gonna be distributed into this part and this part, right? And then we do this from the same part here, which also contains alpha and beta, right? And we subtract one another, we're gonna end up with these two with this expression here, right? This sum here, right? And we taking the integral over the two sphere. If we we're gonna use that the multiplication of y theta with the complex conjugate of y phi is the same as the complex conjugate of y phi here and here, right? These two commute, okay? So in a way that let me just see if this is correct. Yeah, this is correct. So here we multiply by the theta. Oh, okay. There's a mistake here. There's a mistake here. It should be y theta star here and y phi star here. But you can prove that this is completely that they are equal, right? To multiply y star theta to y phi is the same as taking y star phi and y theta, right? In such a way that this element here goes to 0, right? So it is not a mistake. It's not, it is correct. This expression is correct, right? Because this term is exactly equal to what we obtained here. Is a property of this vector spherical tensors, right? These vectors, spherical vectors, I'm sorry. So this term will go to 0, right? And what is left off is only this one here, okay? And if you check into the orthogonality properties, you will see that the integral of on d omega of this object here renders the L times L plus 1, right? So this is how we separate them. This is how we separate, right? This is how we obtain beta exclusively, right? If you wanted to obtain alpha instead, we would have to do another set of multiplications and summations or subtractions. We would need to do another combination of the vectors here, of the tensor parts here. And which combination will you will do? It depends on the vector that is multiplying the functions that you want to obtain. Since here the tensors that were multiplying beta were the SA vectors, right? The odd vector. We looked into what is the orthogonality property that takes the SA vectors to the L plus 1, right? To the eigenvalues of the Laplace of the Laplacian operator, right? And then you're gonna see that conveniently, as you worry about this combination here, this what goes on in the other term goes to 0, right? Because they are orthogonal to each other, right? The SA and the YA are orthogonal to each other, okay? This is why this goes to L plus 1 and this goes to 0, okay? This is why these are the orthogonality properties, right? So this is how we separate beta and obtain beta, okay? Is it clear how we obtained this? Is it clear? I know that the full expression is far from clear, right? You would have to go back to previous lectures and look how the orthogonality properties look like, see how they look like, and see that this is exactly one of them, right? But is it clear what we did so far to obtain beta? Well, if there's no questions about it, I'm gonna move on. I'm gonna stop this lecture a lot and ask, because every step in these computations are important. Okay, but let's
Vitor,
go.
there's a question
Okay.
about João Pedro has a question now.
Mm-hmm.
Please, can you remind me who are alpha and beta?
Who are alpha and beta? Oh, okay. Okay. Let remind you who are here. Alpha and beta are the vectors, right? That contain the first and second derivatives of the even metric perturbations and the odd metric perturbations. So here I presented to you what the betas look like, right? Because this beta here is a vector, right? It's a vector in the sense that there is a beta 0 and a beta 1. This index A runs from 0 to 1, right? The small caps indices, they run from 2 to 3, right? Remember that they run from theta to phi, and this runs from t to r, right? So each component of this vector is an equation, is an equation that contains first and second derivatives of the metric perturbations. In here, we have first and second derivatives of the even metric perturbation, and here we have the first and second derivatives of the odd metric perturbations. Such a way that the betas, for example, I didn't present to you what the alpha looks like. Okay, I'm going to present them to you the next lecture. But here is the first component, beta 0 of the vector beta A, right? Which is this whole full equation here. Okay. Oh, a reminder. Okay. If you try to check this equation and try to compare them with the ones obtained by Berti and by Ferrari, by Valeria Ferrari, you're going to see that they are different, a little different, because here is the completely general equation in the sense that I'm not assuming any particular form or value for f, right? In both Berti and Valeria, they assume that f is equal to 1 minus 2m over r, right? Which is the short shoot function, right? Here, this is more general, right? This is a more complete, in some sense, equation, because it's completely general in the form of f. Okay. If you look into Berti and Valeria references, you're going to see that this element, for example, is taken to be the second derivative of 1 minus 2m over r, right? Which will be some, if I remember correctly, minus 4m over r cubed. But anyway, it's just a matter of plugging f equals 1 minus 2m here, and you're going to obtain exactly the equations of Berti and Valeria. Okay, but I wanted to put this to present this way for you because there is no reference that I could find that present the equations in such a general form. Okay, and I had to develop them to construct the code in Sage Mathematics, in Sage Math and Sage Manifolds to get to these equations to see the dependencies of F, because in my research, what I do to the metric, it changes this function F, right? From the usual Schwarzschild one. So I needed these equations in complete general form, right? And not assuming a particular value for F. So this is why I wanted to present them to you in this way, because I haven't found a reference that does this. So a little bit of a new way to see these equations for you that are joining and participating of the mini course. So okay. So is it clear? Did you was I able to remind you who are the alpha and betas, João?
He said thanks, so I guess that's a yes.
Yeah, okay. So let's move on, okay? So we did this in the left-hand side, and remember, we are not working in vacuum. So we need to do the same thing on the right-hand side. We need to do the same thing for the tensor, for the energy momentum tensor, okay? Which is basically doing exactly the same thing, right? See that what we did here, we will do exactly the same thing for the energy momentum tensor. The 16 is here because we multiply by 2 here, so we'd have to multiply by 2 in the other side as well. So we used to have 8 pi, but now we have 16 pi here, okay? So if we constructed the tensor perturbations like this and this, right? The full perturbation tensor, the energy momentum, the full perturbed energy momentum tensor would be to sum this matrix to this one. I didn't do here because you would have no space to do this. Here is a very convoluted matrix, and we don't need to worry about them, because if we keep track of what is happening on the left side with the Ricci tensor, right? Since the perturbed Ricci tensor is equal to some constant multiplying the perturbed T mu nu, what happens here, we just reproduce in the same manner on the left-hand side, which is exactly what we did here. So we took these components, which are exactly equivalent, right? So we do the same here, and if you do this in the same way, you're gonna see that what is left, it's only the odd part, right, of the vector, of this vector here, the perturbed vector. This perturbed vector has an even and odd parts, right? But the same way that we obtained only the odd part, here we obtain only the odd part as well. Because these components here, this vector, right, for t equal to 0 and t equal to 1, they were multiplying the same basis element that beta was, right? Because we constructed the matrix in this way, right? This is TA for a equal to 1. This is TA for a equal to I'm sorry, this is TA for a equal to 0, and this is TA for a equal 1. And both of them multiply as theta, right? They both multiply as theta here, they both multiply as phi here, which is exactly what happened here. So we separate the same basis element that we're multiplying beta, we're multiplying this element here. So the separation is completely analogous, okay? So you could say that you could only take a look at where this vector here is present in the matrix, in the matrix of the matrix as matrix elements of this tensor here and find who is the correspondent components in the energy momentum tensor. And you would be right, you'd be correct to do so. But this is what is happening, okay? Mathematically, this is what is happening. We are separating them using the orthogonality properties, okay? So this relation here will also yield L times L plus 1 because it is also a vector relation, right, of the orthogonal properties. So in such a way that we get this equation, set of equations, we have two equations here for A equal to 0 and A equal to 1, which become like this, right? This is beta 0 and this is beta 1. Oh, by the way, this F here is in red because it's in the reference for Valeria Ferrari, the general relativity and its applications, it is wrong. Okay, the book is very recent, so the book was first published in 2020. So and I think that it doesn't have a second edition yet. So there are some errors and some typing mistakes there. I think that in the reference, this term is only an F, just like here, right? But if you carry on the equations with an F here, you don't get to the correct Reggie-Wheeler equations. Okay, I have to discover this by myself in the hard way. So I'm giving this to you guys so you don't waste your time looking for the mistake. But if you compare the Berti with the Berti equation, this is correct, okay? But the book by Valeria, there's an error right here, okay? And there is also an error in some of the combinations. In some of the combinations that it does to obtain the equations. But I'll point them out tomorrow, maybe, when we get to the even part, because I guess the error is in the even equations. But okay, so let's go because we have a lot of ground to cover yet. So okay, so here we obtain the two beta equations, right? Beta 0 and beta 1 with the appropriate source component, right? Okay, so you see that here we have a similar equation of sorts as we did for the flat background, in the sense that here we have the second and first derivatives of the metric perturbation, and here we have minus 16 pi and the source. Okay, it's completely different in the form of the left hand side, right? But the idea is the same, right? So for we to separate and obtain T is a little more involved, right? So what we first have to do is define this metric components, which is basically delta R minus, which is a combination of the delta R theta theta minus the delta R phi phi divided by sine squared theta, okay? If we do this combination, so we come back here. I'm sorry. I'm going ahead instead of back here. So look that you see that T is in this quadrant, right? Of the perturbed Ricci tensor, right? So we have to find the appropriate orthogonal relations that will yield all of this and this equal to 0 and this equal to some constant, which depends on L, okay? Okay, so some function that depends on L, right? Just like here, we have a orthogonality property that goes to L times L plus 1. These tensors here, they have a bigger relation. But okay, so we have to see how to turn this elements here into the L's, right? The functions of L, and to zero this ones here. Okay. So what we're gonna do first, we get the set this equal to theta in theta, take the component, corresponding component, take the phi and phi component here, divided by sine squared theta, and take the subtraction, okay? And then we define this, okay? We define this component, delta R minus, which is basically constructed as this, right? Remember that when we constructed yesterday, I think, when we constructed the tensor harmonics, the spherical tensor harmonics, this tensor and this tensor were constructed in terms of this scalars here, W and X, right? So look now that what we have here, right? We have you know how to combine this if you know the orthogonality properties of W and X, right? All you have to do is do the orthogonality property that takes this equal to 0 and this equals to some multiplication of L's, right? And the combination that we are talking about is this. So we take this component here, multiply by W star over sine theta, and subtract with this component multiplied by X star divided by sine theta. And when we do this, okay, when we do this, we get this, exactly this component. This and this, the relation here and here will equal 0, right? Is a combination that will 0 all that are multiplying S, which we don't want, and will maintain T for us, okay? And these are the function of L that we get from the orthogonality property, okay? If you want to remember which one is, how this orthogonality property is, you can look at this, the slides from the previous lecture, which I will send to you today. Okay, so now we obtained the left-hand side for T. Doing the exact same for the right-hand side, we can see is exactly as we did here, right? Just trade this, construct the energy momentum tensor version of this, and do the energy momentum version of this, right? And you will obtain this component here, okay? And then you have your third equation, third odd equation. So now, using the definitions of the three equations, 2 here and 1 here, we have the 3 odd Einstein equations. Okay? Now, you see that we have here, we have combinations of first and second derivatives of odd perturbation components. This H0, H1, H1, and H0 here, right? They are all these 3 equations are combinations of first and second derivatives of H0 and H1, which are exactly the components of the odd perturbation, right? We are not treating with any of these functions a capital H here, neither with K, right? Exactly because what we did was, well, we could have done this 2 ways, right? We could have plugged in here only the odd part of the matrix of the components of the metric perturbation, and turn this machinery on, and then we just separate them. Or as we did, we followed the reasoning of Valeria, of the Valeria Ferrari reference, okay? Where she constructs the full Ricci tensor, right? And we have to, what we have to do is separate them, right? With the orthogonality properties, right? yes, computationally, it's easier to come here and construct two different Ricci tensors, right? And plugging in only the odd and even parts, right, separately, and then turning on this machinery here of these covariant derivatives and see what it spits out, right? But this is a good way to show you what is really happening and what this problem demands in terms of the separation of the angular and radial parts, right? I think this shows more, right? But as I was saying earlier, to obtain these functions, these equations in this form, right? In this format here, completely general in the function f, I needed to construct a notebook on Sage Math to do these calculations from scratch and see and trace the behavior of f, right? And in doing so, what I did, and I'm going to show this notebook for you guys tomorrow. What I did was this: I constructed two different Einstein equations with, in here, I only plugged in only the odd part to obtain the odd equations, and then plugged in the even part to obtain the even equations, which is, I think, computationally is a much more easier trajectory, right? To obtain these equations here. The next steps that we must take, right, is to get to the what we call the master equation, right? Because what we want to do here is put all these three equations into one single equation, right? And to do so, we need to perform some combinations here so that we make either H0 or H1 in terms of the other, right? Which is relatively simple to do, at least in the for the odd part. For the even part is a little more involved and it's a little more convoluted as well. But one can also prove that these three equations are not independent of each other, right? Well, these are the odd Einstein equations, right? So we got to them, right? Which was the focus of this lecture. But let me show you, since we have a little time left, I want to show you some things that we will treat in the next lecture. But first, let me pause and see if there are any questions as regarding what we did to get here. There are any questions? It is important for you guys to try to reproduce somehow, maybe not by hand, but looking at the references, comparing them with what we did here on the slides, right? As once again, be careful with the reference by Valeria, because there's this error here, right? And maybe others there that I didn't find, but so be careful. I would recommend you guys to check the reference by the course, the Black Hole Perturbation course by Emanuele Berti, which is one of the core references that I'm using for this mini course. Compare, because they are in a different form there. Because remember that these are the Fourier transformed versions, right? So all of them here are functions of omega, r, theta, and phi. I'm sorry. These here are only functions of omega and r, right? Because we separated the angular part. So all of these guys here are functions of omega and r instead of t and r. right? But Berti doesn't do this, the Fourier transform. So in here, you're gonna see that there are a few slight differences, which basically are in these terms here with the omega, right? You're gonna see that there are derivatives in derivatives with respect to time as well. Here, all the derivatives, first and second derivatives we have here are first and second derivatives on respect to r, right? These primes here, they represent first and second derivatives with respect to r, right? Berti doesn't do the Fourier transform, right? Right away, at least. So there is first and second derivatives with respect to t, which will in fact render these terms as soon as you do the Fourier transform, right? So these comparisons, this analysis that you make between references are a great way to really get a grasp of what is happening in these equations, because they are very confused and it's very difficult to get a grip on them on the first encounter, right? So once again, is there any questions about anything that we did so far? It doesn't matter if it's in the beginning, if it's something to do with the previous lecture. I don't know. This is the time to ask them. Not the only time, but it's a good time to ask them if you have any. Caio, is there something in the chat and any questions in the chat?
No, anyone hasn't asked any question.
Okay. So I want to take a little bit of this. We have 20 minutes left. I don't want to take much more time of you guys because this was a very intense lecture. I know, very, very intimidating. Well, at least for me, as I was first learning this, it was very intimidating. So I wonder that maybe it is also very heavy. So so only to take advantage of this time and present what we have here. So, well, as I said before, not all the odd equations are independent, and we can show that a combination of beta 1 and t yields beta 0. So if we look here only by looking, you can see that if we take a derivative with respect to r of this equation or of this equation and combine them in such a way, multiplying by some elements of here, I mean, some combination of first derivatives of these two equations will render us this equation here, right? If I'm not mistaken, Bertie tells you which combination is that that does this. But the important thing is that we can throw this equation out, right? Since we are talking about two variables here, right? We have h1 and h0. So it is to be expected that some of these equations are not linearly independent from the other two, right? Yes, this will impose a constraint on the relation of these three energy momentum components, right? But my guess is, I'm not quite sure, but I guess this will work as an extra equation that you can use to determine the sources, right? The differential equations of the Einstein equations for the sources, right? The same way that the Bianchi identity in general relativity, right? The divergence, right? The nabla, the covariant derivative of the Einstein tensor contracted in the first index, it yields 0, which means that the same must happen for the t. I guess a condition of sorts comes out of this combination. But I mean, this is not really important right now. But the important thing is that we can throw one of these equations out, right? In such a way that we can, what is left are these two equations here. And we cannot map this one into this one by some combination of first and first derivatives and so on. Okay, they are completely linearly independent from one another. Okay, and what we're gonna do then next lecture is that we are going to combine these two equations. So we're gonna relabel this and this as A and B to simplify our equations. What we're gonna do is try to isolate H0 in this equation here, right? Take the first derivative of H0 and plug this first derivative of H0 here, right? So that we get a single equation with all the elements that we have, that we have here, right? We're gonna combine these two equations into one, right? And this combination, and this one equation, after we treat it a little bit, and rename some functions here, are gonna yield us what we call the master equation. And in the case of the odd metric perturbation, what we call the Reggie-Wheeler master equation. Okay, and the form of this equation it's very familiar to you, and I don't want to ruin the surprise, so no spoilers, but think about this, what form this could take, right? Since we are talking about something that represents a wave, right? But what must be different from the wave that we obtained, the wave equation that we obtained in the flat case, since we are not working in flat case anymore, right? We are working with a set of equations that are much more complicated. But think about types of wave equations that you know, and I see you guys tomorrow for the continuation of this, where we're gonna get to the Reggie-Wheeler equation, and where we will repeat everything we've done here for the odd equations. We're gonna repeat them for the axial slash even equations, so that we obtain the other master equation, right? The even master equation, which we call the Zerilli master equation. Okay, and then we conclude our course. Tomorrow is the last one. All the things are coming together, season finale, so don't miss it, okay? Because the master equations are the grail, the holy grail of this mini course. Okay, so thank you everybody that came today. I promise that I will try very hard to send both of the slides from today's class and yesterday's. I'm not going to swear on it because I have some stuff to do that I need to do. But I'll try. I promise that I'll try. So you can take a look on both slides before tomorrow's lecture. Okay. Thank you again, Kyle, for the assistance, and see you all tomorrow.
Okay, thanks, Victor. So I'll just stop the recording, and then we can go through some final questions.